let's say we have some object which looks like this. So this is a two-dimensional space, obviously. So we have two variables. Let's call them x and y. And now we want to see in which part of this two-dimensional space we can actually find this object on which the dynamics occurs. This we can do by separating the whole phase space into boxes of equal size. Okay, this does not work anymore. And then we count, okay, how many of these boxes are actually occupied. Okay. You may imagine the rest of it. And now comes the interesting point. If I let the size of these boxes become smaller and smaller, there are obviously more and more boxes needed to cover these geometric objects. But the number which I need to cover this object does not scale in a linear way with the size of the boxes. And that's the important point. There's a non-linear scaling. And we can formally define a scaling exponent called dB by considering the logarithm of the number of boxes of size L divided by the logarithm of 1 by the box size L. And if we consider this for the limit of smaller and smaller boxes, we have what is called the so-called capacity or box counting dimension of this geometric set. Okay, to give you one example, it's geometric example, not time series, Cantor set. Maybe you've heard about in your basic mathematics classes about the Cantor set. It's constructed in a very simple way. We start with some unit interval from 0 to 1. Then we decompose this unit interval into 3 parts and just remove the middle part. Then we take all remaining intervals, again, separate them into 3 intervals of the same size and remove the middle, and so on and so forth. So what do we get? In the 0th iteration, we have 1 interval of size 1. In the second step, we have 2 intervals of length 1/3. In the third step, we have 4 intervals of size 1/9, and so on and so forth. And you will see that it's scaled as follows. In the tth iteration, you have 2 over t of these boxes, or of these intervals in this case, and we have as a box size of 1/3 to the t. So the numerator then reads logarithm of 3/t. So by simple mathematical calculus, we obtain here a box counting dimension of logarithm of 2 by logarithm of 3, or 0.63 roughly. So this is a non-integer, so to say, fractal dimension of this object. Well, the idea is now to transfer this from simple geometric objects to time series. And you can do this in a very simple way, for example, by just doing box counting for the graphical representation of your time series. Yes, so what you can in principle do is, if this is your time series, this was the wrong one, do this decomposition into boxes and count how many boxes do you need in dependence on their size. However, in case of a time series, this does not work for boxes that become smaller and smaller because you have a certain minimum resolution, which is given by the resolution of your time series. So, in fact, box counting is computationally quite demanding, but it does not give you a very good idea of your scaling, just because you cannot approach this limit of smaller and smaller boxes. That's why 20 years ago, in 1988, Higuchi from Tokyo ISM came up with the idea to consider the scaling of the curve length with the embedding dimension as a proxy for the fractal dimension. And okay, this is basically written here, so what you have to consider here is the difference between two embedded vectors of your time series. You sum up over the absolute value of this difference. You have to get some proper normalization to get it work. And then you find that this curve length, independence of this embedding dimension, behaves on average like k to the minus d. And d is now again this fractal dimension in the sense of box counting or capacity dimension. So that's the idea. There's also a third possibility, and it's a bit a pity that I had to skip or go quickly through this point in my first lecture this morning. You can also estimate the scaling behavior in a time series in terms of this Hurst exponent. So Hurst exponent, just to remind you, quantifies whether or not there is long-term persistence in our time series. And there's a very simple relation between the Hurst exponent and the fractal dimension in this capacity sense. That is, the fractal dimension is just 2 minus the Hurst exponent. Yeah, it's not a real universal relation, but it holds for most practical purposes, in fact. Okay, some drawback of these scaling behaviors is that often the fractal properties or this scaling properties depend on time scales or initial conditions. For example, I've plotted here a original result of Higuchi's original paper from '88. So he studied the fractal dimension for magnetic field data from the Earth magnetosphere. So they have been measured by spacecrafts. And what he found out is that, in fact, when there's a fractal behavior, you should see in this double logarithmic scale one single straight line. Yes, so according to Higuchi, it's just a power law. A power law, when you plot L as a function of k in a double logarithmic scale, becomes a straight line. But Higuchi found that there are, in fact, two scaling regions with a certain crossover time scale. And such a crossover time scale can be understood as the result of a characteristic frequency, again, which is in the system. So in his example, there was some characteristic period of about 3.25 seconds. I'm not aware of any physical meaning of this time scale, but it's a robust time scale, which you can also see in the power spectral density of the system. So the point is, if you have a characteristic frequency in your system, then you usually do not have only one, but at least two different scaling regions.